Thank you very much for inviting me to speak. That was nice. Really pleased to be here and be able to do that. So, yes, I wasn't sure what to talk about, and I gave actually two options to run. He didn't choose, so I had to. So this is now my choice. I thought because this is sort of a crossover between topology and representation theory, I dare talk about this topic. I'm not a representation theorist, of course, and this is a very new topic. It's really quite basic in many ways. Maybe not a bad thing, just for the whiskey tasting, but I hope it's just to, when you look at things from such an applied point of view, you are revisiting certain notions, and of course they are relatively basic at first, but sometimes they also might lead to new ideas in in the application area, but also in maybe the more theoretical side. So before I forget, all of this is joint work with Mark Verstand, Emil Jacquard, and Nanda. And so let me first say something about TDA. So if you haven't heard about this, this is a crash course of 1 or 2 slides. Persistent homology is the key, the main tool in data analysis. The idea is to start with a point cloud on the far left, and then as epsilon grows, this is the real line, the black line, you associate complexes to it, which are the vertices Rips complex. Close by, epsilon close by points are connected, and you fill also them with simplices as soon as all the boundaries of the simplex are already in your complex. So that way, as epsilon grows bigger and bigger, the thing that as a point cloud might look like a circular shape will certainly have the homology of a circle. But then, of course, when your epsilon is too big, the simplices are going to encompass all the whole hole, and the homology becomes true. So it's a little bit difficult to see. There's a blue and a sort of a purple set of lines. The blue lines track the H0 of the homology. So when you have the point cloud, you have lots and lots of points. You start with lots of blue lines, and of course, once you are at the end here, you just have one component. So that's how we see the H0. H1, there might be some funny things going on, nearly arrows, and so there's a little short bar at around 0.6, and another short bar, and then of course one long one, which tells us represents a big hole of the circle-shaped complex that we have. And this is a persistent homology. This hole, as we include the complexes one in the other, that is persistently mapped to a non-zero element. So these bars are representing generators in the homology at a certain start, at a burst, and the end, and when they actually go to 0. Now, that now gives us some sort of summary of the data, which you might be able to do statistical analysis and use in more general data analysis. Now, there are 2 things that, let's see, maybe formally we can think of persistent homology, therefore something on the line Z as an ordered line, we apply vertices Rips complex, and then we get the apply homology, and we get these vector spaces. Now, this whole thing is predicated on 2, I think, main theorems effectively. Namely, you are able to write things as bars, and so that is a very nice visual summary. And then the second one is that if you change your input data, you only want to change a little bit the output data, namely the bars, and both of these things hold. Now, there is one problem, however. When I said you can change your input data, I only meant you can move the points a little bit. What you can't do is just put something in the middle of your circle, just one point. You might say, if there's a million points, and put one point in the middle of your circle. That is only a small change. However, that does mess up your system homology. And so here you can see these circles are just two different types. They're not quite, the points are not quite sampled from circles. There are actually some mistakes, maybe some misreadings, some learners. You want to still recognize these as circles, but you have these this problem of these extra points inside the circle. And TDA has struggled with this, and the solution, one of the solutions anyway, is to say, well, actually, I look at two filtrations. One is my epsilon growing and growing, but then the other one tells me which points I'm going to include, and it's really the density of the points. So if there's a lone point, I'm not going to put it in immediately. I'm only going to put it in if it has at a certain density level. And since I can't choose the density level, I need to include all density levels the same way. I didn't want to choose a radius, an epsilon, so I include all of them. So in B, you see actually these simplicial complexes. I'm not sure how helpful that is, but maybe in C, these are actually activations of the different homologies that you can see. So the first panel, you can sort of clearly see three different circles. This is a landscape panel, and then in the other one, you see the bigger and the smaller circles. So I want to explain this in much detail. This is a panel from a paper where we studied the interpretation of drugs effectively going into the center of a tumor. So we really need to understand pictures like this. Anyway, so the point being is that we need more than one filtration and double filtration. So mathematically, this is now a multiparameter persistent homology. And it goes from Zn as an ordered set to simplicial complexes, and then to biohomology into vector spaces. Now, it is now robust against outliers and misreadings. The problem, however, is that the math is not so easy. So we don't have an easy summary like we have the barcodes. And that has been one of the big themes in persistent homology, to try to understand this multiparameter persistent homology and come up with good vectors. So that's the introduction, why I'm looking at this particular problem in this particular way. So we had some ideas earlier. So the new idea here is to use quiver representations and something called Harder-Narasimhan invariants. So I'm going to step back. This is going to be 101 for quiver representation, and I probably for half of the audience, hopefully not the other one. So quiver representations. What we do is we take a quiver that's just a directed graph. Q0 are the vertices, Q1 are the edges, and We can associate a category to that, where the paths in the quiver are your morphisms and the vertices are your objects. And we define a quiver representation as a function from that category to vector spaces. And vector spaces are always a thing of finite dimension. Just look at finite dimension. So, in particular, to every vertex in Q0, you associate a finite dimensional vector space. And for every edge, we have a linear map. That's a very straightforward thing to do. Now, example, which will be used later. Say I have some subquiver, Q dash of my quiver. Then I can form the so-called identity representation, where I just associate to every vertex in my subquiver the one-dimensional vector space F, and to every edge that is between two non-zero things, I assign the identity, but 0, right? So it's sort of defining an interval, basically. These are very simple modules. Another one that seems to have not been studied for some reason, but maybe I haven't looked at it or talked to the right people. We are interested in looking at one vertex, looking at its vector space, Vx, and just looking at the smallest representation that contains that. So, in other words, the representation generated by this vertex X, okay? What flows from there. And that's another sub-representation. Okay, so when Q is finite, it's well known there is a unique transition into indecomposable, so V can be written as some multiple dVi, where I is one of these indecomposable modules in the representations of Q. Okay, and then Gabriel's theorem, so it goes back a long time, 50 years or more, says that the indecomposable, the set of indecomposables is finite if and only if the underlying graph of Q is finite. It's a finite union of simply of type A, E, or E. I mean, those are the simply laced ones. So in other words, the representation theory is nice in these cases, and otherwise it's so-called wild type. And if we think about back to persistent homology, ordinary persistent homology is just going along line, and that's AN, and so that's nice, and that's why we had our barcodes. Zigzag is also okay, because that's also AN, it's just on a line, only that the arrows are potentially in opposite directions. But multi-persistence, according to this, is not. So we need invariance. Right. So in our search, we now look at the Harder-Narasimhan filtration. How do we do that? I'm going to go step back and be a little bit more general, and then come back to what it means in quiver representations. So this is something that holds quite generally, and I guess has been very much popularized by, in the more general sense, by a paper, a very important paper by Bridgeland. We take an abelian category, and the stability condition is just a homomorphism from the K-theory of that category to C. Only we take the half plane where the reals are positive. So we take this as a good homomorphism and define a slope. So this is Z of V is a complex number, so we can take the imaginary and the real parts, and we take define the slope for every V non-zero. Okay. Now V is semi-stable. It's just a definition. If this slope is always bigger for any submodel. Bigger or equal. And it's stable if it is strictly larger for any sub. Okay, so these are somewhat abstract conditions that at the moment we just maybe take in. Now, with this stability condition, we have the following theory. If C is reasonably finite, meaning that it's both Noetherian and Artinian, so we don't have infinite changes up or down, then every non-zero V admits actually a unique filtration, such that the quotients are semi-stable and their slopes satisfy this inequality, this strict inequality, which is quite important. So of course, we are mainly interested when C is the representation category of a quiver. And as long as the quiver is finite, indeed, then this category is Noetherian in acting. Okay, so in other words, our persistence modules, we can apply the seven. Right. Now, how do we get these stability conditions? They are a bit abstract at first looking, but actually we can narrow it down. For every representation, and hence this defines the homomorphism from the K-theory, every representation I can assign to every vertex simply the dimension of the representation at that vertex, of the vector space that I get at that vertex. Okay? So that defines me this dim, just taking dimension at every vertex. Now, as long as the quivers are actually acyclic, and acyclic means in the directed sense. So in other words, there's no directed cycle in the quiver. Okay, I can't go around and come back to the same vertex in the oriented way. Then actually this is even an isomorphism, right? So the some of the case theory, all the interesting bits, the maps are sort of gone. Now, it's quite reasonable to assume that our stability functor therefore factors through this dimension factor. Indeed, I will be mainly interested in acyclic quivers, so that's actually an isomorphism here. So our stability condition will have to factor through this because it's an isomorphism. So then the stability condition, we can now write it as a homomorphism from Z to Q0 to the right half plane. And so really, we're just looking at two functions, namely the real part and the imaginary part, which I call beta and alpha here. Now, again, it's probably not surprising. The real difference is in the relation between alpha and beta, because ultimately we are just interested in the slope. So actually, we don't lose a lot if we just assume that beta is always 1. Okay. So the whole thing is now we are interested in the central charges, alpha. Everything Z is completely determined by that map from Q0 to R. And in that case, also our slope has a much easier formula, namely on the bottom, I always have just a sum of all the dimension at every vertex. So that's you might say that's the dimension of the representation. And on the top, I have these weighted sums of dimensions. Now, the Harder-Narasimhan simply Hn type of the representation we can now define as these dimension, dimension vectors, I guess, effectively, of the subquotients. Remember the SIs, you have the filtration, V0, V1, etc., and the SIs are the subquotients. So we just take those and all the dimension, and that is the so-called Hn type. Okay. Right, what can we do with that? Of course, you might ask, how well does the HN type distinguish between modules, representations, and we say alpha is complete, also we have one for every choice of central charge alpha. We call it complete if indeed it's the HN type is the same, if and only if V and W are isomorphic. And the proposition is that alpha is complete, then every incomposable representation, and where Q is alpha stable, and indeed generally also vice versa. So let's look at an example. Where might we get some interesting charges from? One was suggested and came from a paper on Swedish really. You can think of a representation, a quiver representation, as a sheet on a cellular sheet on the graph, underlying graph. And so the Euler charge here is just simply defined as taking a vertex X and saying I take 1 minus the number of in errors. And with that charge, it's actually related to the Euler characteristic of the sheet that you get. That's just for motivation. It's a simple enough definition, I think, and it makes sense that one might want to look at it. Another one that we came to think about, and I think, again, this is something that maybe traditionally haven't been thought about. It's just a skyscraper, right? You have all these vertices, and you might want to understand what happens at one vertex, so you put a weight there and forget everything else. So that's the skyscraper, just a better function. All right, so now with these two, I want to go through a couple of examples, what this actually translates to, and then continue maybe what we can really say. Okay, so ordinary persistence. We just have even equi-oriented row of maps, and we take the Euler one, but of course in this case it's just the same as putting the skyscraper at the first vertex. And the theorem is that indeed what you get is the dimension of these quotients, these dimension of these sub-quotients, so S K is a K sub-quotient, at vertex xi, I'm going to have this evaluates to the number of bars in my representation that go from 0 beyond xi, maybe it's jk. So really, I'm detecting quite a few things, but I'm ignoring everything. I can't see anything that starts after x0. So I can't see anything of those. And the other ones I can now recover and inductively from this information. Okay. So in particular, it's not complete, yeah, because I forgot all the bars that start later. Kinzer, in his paper in 2022, actually determined all complete charges for AM. And as a corollary, what one gets, a charge of, so in other words, a mapping from Q0 to R is actually giving us a complete invariant, if and only if we have the inequality that the source, in other words, it's increasing, I guess, the source of the edge has a higher slope than assignment, right? And similar, it has been, complete charges have been determined for these other types, D and E. All right, so that's a complete picture, really, and makes some more sense. And of course, sorry, I should say, we completely recover everything that we might want to know. Right, now, circular persistence. Maybe the first one that is not so straightforward is when you try to put this down here. Here you have the first AN, and here it's the second one. So the last one, the xn minus 1, has a map back to x0. So that's what this is. And the black circle here is the vertices arranged in a circle. And here I'm trying to demonstrate the two different types of indecomposable modules that you get in this situation. One is where you take just a long interval, u to b, and you wrap it around your circle. You start at some new dash, which is the same as u modulo n, and similar, you end up at something v dash, which is also equal to v multiplied. And of course, I can go around many times, but this is a type of module that is composable. Yeah. So at this point, I have the vector space has dimension 2, as it does everywhere here, but then it goes down to 1. And the continuous line says that I'm picking the identity between all these maps. Now here, there's a second indecomposable module, which is, well, I pick a W. Here I have the W is 2, namely dimension 2. And I have the identity all the way through until I have to close back to x0, where I have to use a non-trivial matrix, and indeed I can take a Jordan block of size W with lambda from the diagram. So that is a theorem that these are the only indecomposable modules, and indeed we can understand these quite well by basically unrolling them, and so we get an infinite periodic infinite quivers and understand them that way. Now, basically, this is the information you can also get out of the H and type. I won't go into details, but basically, when you unroll these W's, you only see infinite intervals, infinite lines. And of course, you completely lose the information of lambda and okay, so this is just packing what I just said in the film, and I might actually skip this and jump on. So in particular, as we expected, the invariant is not complete. Right, so now I want to go back to this skyscraper invariant. So we've seen that in the AN type, it actually detected pretty well everything that started at x0. So the idea then was, well, why don't we just look at every point and then just combine them to 1? And that's exactly what this skyscraper invariant is supposed to do. More generally, we can of course do it for every quiver. And what do we see for every quiver is following. So Q is just completely general here. And we have an H infiltration along some skyscraper delta X. And what do we get in the filtration is the following. Let J be the smallest index where actually we have the complete vector space at X, okay? Now, then it has to be that it is actually the top one or maybe the next one. So those two are the other cases. Now, if I look at something that's below J or equal, then I have actually that this filtration VK here is just generated by that node. Okay, so it doesn't have to be the whole, of course, but it is generated by that. So after the first step, we only see things that are generated at X. And here's a very quick proof, effectively, you know, delta, this is our slope. Remember, we have just one to look at. namely at x, so it's just the dimension x. And then here we have the dimension of the whole representation W. Now, if we have, this is trying to prove one, if we have actually that Vxj is the same as Vx, then of course the quotient, the top quotient here, will have to be 0, okay? Because we're only seeing a vector space at x, so it will be 0. Now, at the same time, these slopes have to be strictly decreasing, so it only leaves us with one or two possibilities, and JA and JL minus 1. And for the second one, well, if you start with V1, by definition, or by the theorem, it is semi-stable. Now we can compare it with the submodule just generated by what's at x. And then we look at their slopes, but the slopes again have to be decreased. The submodule has to have a bigger one, and it forces all these dimensions to be exactly the same dimensions as the one we get from one generated at x. So it's a very simple argument, and then by induction you get the theorem. Okay. As I said, we understand the skyscraper quite well, and we know it gives us interesting things for AN. So why not now considering them at all places? And indeed, it's easy to see that for AN, this is now a complete invariant. All right? Now, how does it compare to other invariants? We are not the first one to think about it. So the rank invariant is one that was actually defined right at the beginning by Carlson and Zamorotton in 2007 when they started the study of multiparameter persistence homology. And they define, well, okay, at least let's do something very simple. Given any two vertices, I can understand what happens to the image. I just want to understand the rank of that image now. And in our language, we can formulate that as, I look at the submodule generated at x, and I just look at the dimension of what happens at 1. That's the image. So this formulation just then also completely generalizes this rank invariant to any quiver. And indeed, the skyscraper invariant is strictly stronger than this invariant. This here is the formula how you can actually recover the rank from just these modules, the quotient modules in the HN filtration. And then to show that it is actually stronger, well, you need to do an example. And here's the example, very simple. F2 F projection of the first, projection of the second, and compare that with where you have both these arrows to be the projection of the first coordinate. Now the rank invariant just looks at, well, rank here is 1, rank there is 1. Every rank is of course exactly the same as in this picture, so the rank invariant are the same. However, the HN invariant are going to be, so the skyscraper invariant are going to be different, because here I have the non-trivial submodule, this separates into a submodule that's just F identity and then 3 identities. So that is detected by the skyscraper. Now, since 2007, there have been other attempts, and possibly one of the more successful ones is this generalisedrank invariant by Kim and Midmoli in 2001. They have a paper. So what let's say is actually, well, rather than just looking at fixed points, I'm going to look at any subquiver and take the rank, of the canonical map from the limit to the column. Okay, so because I do it for every sub-quiver and restriction of B, this gives me a lot of new invariants. And indeed, it's clearly stronger than the standard ranking variant. Here, they defined it in the multiparameter assistant setting. You can do it for any quiver, it doesn't have to be commutative, etc. So it's a small generalization. And indeed, you may have the theorem here that I thought, well, the skyscraper and the generalized ranking invariant are not comparable. In other words, neither of them are stronger or weaker than the other. And here are a couple of examples. Again, they're relatively simple. For one, the generalized ranking invariants are the same, but the skyscraper are different. And here we have an example where the opposite holds. Hopefully, yeah, maybe part that's interesting here is that the ranking invariant, here we have things that are sort of starting at the same point. Something that I can partly see where the ranking invariant is final, because here we always see things that are generated at different points, while the general ranking invariant is final on things that are maybe having endpoints here. So to the target. Okay, let me just move on. So one other thing that we then, it's something that you're free when you apply something new and try to think about new things, and from an applied point of view is you might want to understand, well, maybe I can't distinguish between all the modules, but maybe there's a subset where I can distinguish them. Yeah. And this is sort of the idea of restricting now your category. So I have a quiver, and I can now look at the subcategory generated by all the identity representations. Okay, so remember, these are the representation that is just assigns the one-dimensional vector space to every vertex in the subquiver and an identity to every edge in there. Now, that of course generates a subcategory, and I can ask myself, is my invariant complete there? And indeed, Mimoli and Kim proved that for grid quivers, so the ones that come up in multi-parameter persistence, this is indeed a complete invariant. And that theorem and also the proof easily generalizes for this more for the GRIs defined on any group. So that's helpful. One thing we haven't yet been able to do, which is an obvious open question, therefore, is to understand what is the maximal subcategory where the skyscraper is a complete invariant. So somehow characterize where the skyscraper can tell us something more. Okay, so if we restrict our category a little bit more, namely, think about this grid quiver, which does come up in multiple systems, and we look at only shapes that are really rectangles, so of this shape, then we can look at the subcategory of representations that are just generated by such rectangles. Yeah. That's of course everything in the one-dimensional case, but in high-dimensional. Now on this category, it is now it can be shown that the central charges for large class, I'm going to say something more about that. This alpha is going to be complete if and only if it satisfies this condition that we've seen basically before, namely the alpha evaluated on the source of an edge has to be bigger than alpha evaluated on the target. And that's true for every edge in our quiver. That's a non-trivial theorem. I haven't said what H is. H is a sort of avoiding certain hyperplanes in all possible charges that you might want to define. So I'll leave that as a technical thing. It's a set of measure zero, I guess. And so the usual sort of things happen. But the proof for this is quite intricate. It uses some lattice theory, but also something we are expected to learn, namely the max flow minicut theorem from combinatorics. Okay, and this is actually the main reason why, for example, we haven't tried to prove this now for other types. Okay. All right, so I'm going to finish now. We have a new invariant. It seems to be stronger or as strong as some other invariants, gives us some more information. So the immediate question, of course, is, since we are looking from the applied point of view, does it have stability? And the answer is yes. One has to put ourselves into the right framework. So rather than talking about z to the n, we will talk about r to the n, and have measures on it. And yes, it is does have stability, and it's actually a paper that Mark put on the archive, I think, just recently. I think it's on the archive. And so that's good news. The other news is, or the question you asked, what about computability? Again, in order to apply, you need to be able to compute. And there are some results in these directions, namely that it is generally polynomial. Mark has some software, but he's not yet willing to publish it. So there is more work to do, but it is computable, and these things on that side in particular always improve with time. So I'm going to stop here, but maybe leave my thanks to collaborators and yeah. So thank you very much.